Howdy, folks. Thanks for checking into Mr. Ulrich's Landofbiology.com. I'm Mr. Ulrich. In this video notes cast, I'm going to reintroduce the concept or the topics involved in biochemistry. And I'm also going to get into some water chemistry as well. It's important for us to, as AP students, be able to discuss on a structural level the biochemistry of the cell membrane and other structures within the cell and how they work. And so we're going to need to have a common language to do this. Science is, by its very nature, empirical. That means it tries to figure things out by breaking them up into smaller bits and then learning the properties of those bits and how those bits go together in order to create the properties of the whole. Now, when we start breaking larger compounds apart, molecules apart, we yield atoms. Each element, as we see here in the periodic table of elements, each element has its own characteristic number of protons, and that gives the element its properties. They're arranged this way in the periodic table. Mendeleev recognized that there is a pattern based on the number of protons. There's a pattern to the reactivity to the chemical properties that the different elements have. Now, phosphorus was first discovered by this guy, Hennig Brand. Hennig Brand, like many researchers of his day, was trying to figure out how to turn lead into gold. So he had his big idea. He had a great idea. His idea was to get a bucket and then pee in that bucket and save the pee. And he just saved the pee for a long time. And as the water evaporated from the urine, water contains phosphates, and through chemical degradation and natural breakdown of those materials that were in urine, it started to glow. And that's where the name phosphorus comes from. Now, as biologists, we don't have to really concern ourselves with all of the elements here on the periodic table. There's just a few that we are mostly going to be talking about. The science of Einsteinium is not really pertinent to biochemistry so much, but carbon, nitrogen, oxygen, phosphorus, sulfur are certainly important. Hydrogen, ubiquitous. Sodium, magnesium, potassium, and calcium. All of these are going to make up the vast majority of the compounds of life. It's not exclusive. Zinc is important, iron is important, selenium, there are plenty of other things that we need, but these are the major. When we start looking at the different elements and their characteristics, we see the pattern that was noticed by Mendeleev and others. It seems to correspond to the number of protons that were in each element. One of the major players here was not actually the number of protons, but the number of electrons that are whizzing around the outside, most notably the electrons that are in the outermost shell of the atom. If you remember back to chemistry, this is where the octet rule comes in. And we can arrange these atoms in columns based on the number of electrons they have in their outermost shell. We call those the valence electrons, and it does give them similar chemical properties, especially bonding, covalent bonding properties. The number of valence electrons that an atom has a direct impact on that atom's reactivity, on that element's reactivity, the number of bonds it's going to make and how quickly it makes those bonds. Because atoms want to have a full valence shell. Now, if that's the first valence shell, that's 2 atoms. If it's the second or third, there's going to be 8 electrons whizzing around there. So if they have a partially filled outer shell, it's only got 1 or 2 in the second or third shell, it's going to try to lose those. If it has almost full valence shell, then it's going to try to pick up a couple other ones. So you can see if there are atoms, there's one atom that really wants to lose an electron and another one that really wants to gain an electron. You put the two together and they can kind of switch it back and forth, switch it back and forth, switch it back and forth, switch it back and forth. And that sharing of the electron is what forms the covalent bond. So these two hydrogen atoms here are quite happy because they both have two electrons in their valence shell. Um, they're sharing those two, but sharing is caring. The properties of the atoms, the elements that make up larger biological molecules, are going to give us some of the information, some of the properties of those molecules. We also need to know how those are bonded together. Since most of the elements in living things are nonmetals, carbon, nitrogen, oxygen, phosphorus, sulfur, and hydrogen, they share electrons with one another to complete valence shells, and they form what are called covalent bonds. Now, there are other bonds that are important, like hydrogen bonds, but we're going to talk about those in the next slides to come. A couple more words on covalent bonds. They come in a couple varieties, depending on the nature of the atoms that are sharing the electrons. They can either be polar covalent bonds or non-polar covalent bonds. And it all has to do, like I said, with the properties of the elements, how electronegative they are. Uh, if there is no difference in electronegativity, like between carbon and hydrogen, which have the same electronegativity, that means they share the electrons equally between the two, and there's no unequal distribution of charge. And that makes those molecules nonpolar. Also, because of that unequal distribution, because of the equal distribution of charge, it makes those compounds pretty stable, and stable compounds make for good building blocks of living things. They don't break apart. It takes a little bit of energy to make these compounds. That means that when the compounds are broken apart, they release that energy and have quite a bit of it. Um, Elements and atoms are all well and good. But as biochemists, we're really concerning ourselves with the molecules that are made of those atoms. Uh, Water, of course, is a pretty fundamental molecule, especially when it comes to life. When we look for life on other planets, one of the things that is looked for is water. So as biochemists, we need to be familiar with the properties of water. There are several that we should know about, things like its polarity, hydrogen bonding, the way that it adheres and coheres, so adhesion and cohesion, the fact that it has a really high specific heat and high heat of vaporization, and that ice floats. All of these are kind of neat things about water itself. Now, I mentioned earlier that most of the biological elements are nonmetals and they do share electrons between one another. That is true, but not all of them share them so fairly. Oxygen actually likes its electrons more than hydrogen does. So where in carbon and hydrogen they have the same electronegativity and they share those electrons fairly, oxygen has a much higher electronegativity and it doesn't share its electrons as fairly. What this does is it makes water a polar molecule. Now, what do we mean by the poles? Well, kind of like a magnet. The Earth is a large magnet, and it has a north end and a south end. That's the poles. You can think of them as a plus end and a minus end, like a battery. Well, oxygen, because of that, because of its high electronegativity, kind of hogs some of the electrons to itself, and does make for the oxygen to be a little bit more negative than the hydrogens. It's going to pull those electrons from the hydrogens. And so really all that's left hanging out there with the hydrogens is just the hydrogen nucleus, which is one proton, one neutron. And so you get this positive charge on the hydrogen side and negative charge on the oxygen side. So we get poles just like in a magnet or on the planet. This polarity, the polar nature of water, It was one of the reasons why we call it the universal solvent. It is really good at dissolving all kinds of different substances. Speaking of universal solvents, we should have a couple words here about solutions just so we can make sure that we're using the same terms and know what we're talking about. So when we're talking about something dissolving, here's some sodium chloride or table salt dissolving in a beaker of water. This is able to happen because as the sodium chloride kind of falls apart, it can because the chloride, negative chloride ions are surrounded by the water molecules, and the positive sides of the water molecules will stick to the negative chloride ion. Where the flip side of that, of course, is that the positive sodium ions get surrounded by the uh, water molecules where the kind of the more negative oxygens of the water molecules kind of stick to the positive sodium ions. So, because most of the beaker, however, is water rather than salt, we refer to the water as the solvent and the salt to be solute. The salt water that is made is referred to as the solution. So if we look at this, it's solvent plus a little bit of solute. So lots of solvent, a little bit of solute yields solution. Another important property of water is its ability to form hydrogen bonds. Hydrogen bonds are those electrostatic interactions. We're not sharing electrons here, but it's an electrostatic interaction between the negative-ish oxygen and the positive-ish hydrogen of a neighboring molecule. Now, they don't have to be water molecules, but certainly can be and often are between water molecules themselves. Now, this doesn't involve sharing electrons, so it's relatively weak. Each individual hydrogen bond is pretty easy to break. They break just by smashing into one another. However, these are the bonds that hold your DNA together. And if you think about it, it's kind of important for the bonds holding the individual bases together to be weaker than the bonds holding the backbone together, or the bases themselves together for that matter, because the DNA needs to be able to unzip easily and reanneal to come back together again. We don't want the side chains to the backbone to break apart very easily. That would be a big problem. So though they are weak, there is strength in numbers, and that of course is the bluegrass band strength in numbers, who are not very weak at all. These hydrogen bonds are going to cause attractions between particles. When those particles are the same, like two water molecules, we call that cohesion. The water molecules here on the surface of this solution water here are sticking to one another through hydrogen bonds. All right, and the force of those hydrogen bonds is holding those molecules of water together, creating like a skin. We call this surface tension. And in the case of water, that surface tension can be strong enough that it can support the weight of a very carefully placed paperclip, which is certainly more dense than the water and should certainly sink. It's also the force that holds up water striders like this. Now, in the case of this water on this leaf, the water is certainly sticking to the other water molecules. What it's not sticking to is the different molecules, the molecules that make up the cuticle of the leaf. When we're talking about attraction between different types of particles, we call that adhesion. Just think of adhesives like glue. So water, in this case, is not adhering. It's not hydrogen bonding to the waxy cuticle because, of course, wax is nonpolar, and water can't hydrogen bond with a nonpolar substance. Water can adhere to things like your finger. It will also adhere to glass and cause that meniscus that you, of course, read from the bottom of the meniscus. What this force of adhesion and cohesion is also going to bring about is something called capillary action. All right, capillaries are very small tubes, and since water will adhere to the side of the tube, it will kind of that the power of adherence can actually stick higher in the tube than the level of the water, and then that adhered water molecule will draw up water from below it, and that's how you get that meniscus. If the tube is thin enough, it will pull water up the tube to a certain height. I mean, eventually the force of gravity is going to be more than the force of adherence and coherence within the water, and it's not going to be able to get all the way up as far up. But this does explain partially how some water is drawn to the tops of trees. This action of water is being pulled through through narrow tubes. It's not the main workhorse. The main workhorse of getting water up trees is this process of transpiration, which we will talk about at length later on. Transpiration actually involves the evaporation of water from the leaves up in the top of the tree. And that negative pressure from the loss of the water kind of draws water further up the tree. But we'll have up the plant. We'll have more words on transpiration later on. Another important property of water is its high specific heat. Specific heat is defined as the amount of energy that is required to bring 1 gram of that substance up 1 degree centigrade. In the case of water, it takes exactly 1 calorie of heat to raise 1 gram of water 1 degree centigrade. Now, that might not sound like a lot of calories, but it's actually more than most things need in order to raise 1 degree centigrade. To see an illustration of this, just think about going to the beach. When you step off the boardwalk and start to walk towards the beach on a hot summer day, where are you trying to get to? Of course, you're trying to get to the water because the sand is really, really hot and the water is not as hot. But when the nighttime comes and you got to put on your jacket, it's kind of, if you didn't have a jacket to put on, if you went into the water, it would feel a little bit better. Because the water is actually going to be warmer than the air, and the sand is going to radiate the heat back into the atmosphere. Another, it's closely related to its specific heat, is the heat of vaporization. Right, this is the amount of energy that it takes for a phase change to take place. So either boiling or melting, freezing. These are both changing from one phase to another. And as you can see in this diagram here, once we get up to this region here, the temperature stops going up, even though we're adding a whole host of energy. That energy is not making the temperature go up. It's going into causing the hydrogen bonds to break so that they can break apart and the water can turn into a vapor. Why is this important for us as biological systems? Well, sweat is created not just to make our lives miserable. It's actually supposed to help us out by cooling us off as that sweat evaporates, as the water changes phase from liquid to a gas. It actually is taking the energy from our body, the heat from our body, to do that. And as the water absorbs the heat and changes phase, we cool off. Of course, that only works when water can evaporate. So up here in August, in the Northeast, when it gets to be 95% relative humidity, sweat just doesn't work, and it's pretty darn miserable, isn't it? Now, the last concept, or the last property that we'll talk about, is density of ice. If we look at these two things, which one would you say is ice? The left one or the right one? And now think which one has more holes in it. All right, so we can see the holes right over here in this one. Here's a hole, here's a hole, here's a hole. These are gaps, right? So this one over here on the left is certainly less dense. And that is the ice, right? That's the frozen stuff. As ice freezes, it creates what's called a crystal lattice structure. And that crystal lattice structure actually takes up more space than the liquid water does. The liquid water can pack together much closer than the ice can. So in this case, the ice floats and the liquid water sinks. When we look at this on a curve, you can see that right about at a little over 4 is where we get the peak intensity, 4 degrees centigrade. All right, that means that water that is just above freezing is at its most dense, and water that is a little bit below freezing is less dense, and so it's going to float. That also means that as that ice heats up and melts, it's going to sink. Of course, the sinking of the melted ice water, it has to go somewhere, and it's going to displace the water that's below it and cause that to come back up. We'll talk more about spring mixes later on. Um, Lastly, what we should discuss as something that happens with water is ionization, and that's influence on pH. Um, Ionization is when a molecule breaks up into ions, and water can break apart, even though it's a covalently bonded molecule. It can break apart or dissociate into two ions. Those ions are a positively charged hydrogen ion and a negatively charged hydroxide ion. Right, that hydrogen ion is basically a proton and a neutron. It doesn't have an electron. When it broke apart, oxygen, because it's such an electron hog, took its electron with it. And so now that hydroxide ion has an extra electron, where that hydrogen ion is missing an electron. Because water makes equal amounts of hydrogen and hydroxide ions, sometimes called hydronium or hydroxyl. Though we talk about hydroxyls, that's really a functional group. It should be bonded to something else. Anyway, we'll talk more about functional groups later on. Because water makes equal amounts of the H and OH groups, it is what we say pH neutral. All right, it has a pH of 7. Anything that throws off that balance of H's to OH's is not going to be neutral. If it's something that contributes more hydrogen ions than hydroxide ions, all right, or at least yields more hydrogen ions, that solution is considered acidic and has a pH that's less than 7. I know it's weird. More acidic gets a lower pH. Counterintuitive, but it works mathematically. When you end up with more hydroxide ions, more OH ions, that solution is considered alkaline and has a pH greater than 7. Speaking of pH, we should have our last final words here on buffers. All right, buffers are weak acids or bases that react with stronger acids or bases within a certain range to prevent big changes in pH. So they're going to kind of neutralize for a certain range of pHs. They're going to quickly neutralize those strong acids or bases. They typically have a rather narrow range of buffering capacity, um, but they are very important in maintaining homeostasis. Our blood pH is slightly basic, a little above 7, 7.35 to 7.45. And that needs to be maintained. And when you start doing exercise, that creates larger amounts of hydrogen ions in the bloodstream, and that drops the pH, and you start getting acidosis. And so your body has to respond. It's going to breathe heavier, and that gets rid of some of it. It's going to excrete it in the urine, although that takes a little bit more time. So there are ways that our body can get rid of it. Of the excess hydrogen that's created. But primarily, it's going to use this bicarbonate buffering system in order to keep the pH at the optimum range. Well, I think that's going to be enough for now. Thanks again for checking in. Feel free to review and go back and watch this over again if you can tolerate it. Email me with any questions, and we'll see you in class.